Thank you everyone for making it for my talk. My name is Joanna Nanjeche, and I'll be talking about a Rust-based garbage collector for Python that we've been working on for a little bit over a year. In terms of affiliation, I do research in an IBM lab at the University of New Brunswick in Canada. A little bit more about myself is that I'm a Python core developer. I've been a Python core developer since 2019. And in Python, I work on the CAPI and sub-interpreters. Last year, I was very privileged that the Rust Foundation funded our work for a period of 12 months to work on this Rust-based garbage collector integration inside Python. I served as a PSF, Python Software Foundation Director for a little bit over 2 years, and currently do research as part of my PhD with IBM in an IBM lab, and do several collaborations. So in terms of expectation, I'm going to start with a brief background on garbage collection for people that are probably not very familiar with the subject. I will talk about the Python implementation where this work was done, and then I will go into detail about the actual garbage collection framework that we use called MMTK, which is Memory Management Toolkit in full. I'll also go into much detail about the integration of MMTK into PyPy. So what's garbage collection? It's a form of automatic memory management. We basically take away, not power, but we take away the responsibility of managing memory from the programmer. Memory management or automatic memory management in the form of garbage collection is a very old field. It's been around for 60 years. And the first garbage collector dates back to the Lisp days. The first GC was implemented in Lisp, and currently very many languages support some form of garbage collection, Python and many other languages. So today I will adopt the normal common terminologies in garbage collection as launched in different literatures, but also the terms we use in communication in the different communities. So whenever I talk about collector today, I'll be referring to the aspect of reclaiming memory for unused memory. And whenever I talk about the mutator, I'll be referring to the application program. So garbage collectors are always classified into three main classes. So we categorize garbage collectors by how they allocate objects, how they identify unused memory, and the methods for reclaiming that memory. So in the early days, in terms of allocation, we can either allocate objects contiguously in memory or through a free list. So contiguous means we allocate objects in the order in which they come. And then free list, we basically maintain several cells in memory of a specific size. And then when an object comes in, when there is need to allocate an object, we look out for a specific cell that matches the size of an incoming object. And then identification of garbage, we can either trace the object graph. So tracing garbage collectors have their origins there. Or we can keep a reference count of a given object so that when the reference count drops to 0, we can reclaim memory. And so also certain garbage collectors are named depending on the way they actually reclaim the memory by sweeping or compaction or copying. So compaction means that when we remove any unused objects, then we sort of rearrange memory to avoid fragmentation and the like. So a brief example is if we have an object graph like this, we have a notion of root sets. So the objects in purple are an example of root sets, and then we'll have an object graph as a program is running. And any objects that have like a hierarchy to the root set are considered live objects. And any objects that don't have that any references that connect back to the root set are considered maybe unused. An example here is object L around here, and object K and N, they sort of reference each other, and we can't map the references back to the root set. So in this case, we could say these are unused, and after garbage collection, 3 objects on this graph will go: object I, object K, and object N. So that's a brief example of what garbage collection is. And then what is the Python implementation that our project was implemented in? So we integrated, or we did our Rust-based GC in PyPy. PyPy is one of the implementations of Python. It's faster than the reference implementation, CPython. The difference is that PyPy is written in Python, a restricted set of Python, but it is faster than the reference implementation because of a couple of reasons. The biggest reason is because it features a tracing JIT. CPython does not have a JIT currently. There is work undergoing for us to support JIT in the future, but for now, most of the performance benefits for PyPy come from the JIT, but additionally, some of the performance benefits of PyPy come from the robust implementation of garbage collectors in PyPy. And so it has like 6 garbage collectors, and depending on the application, you can tune the interpreter to work with a GC of your choice. So we chose to work with this Python implementation because of the history of robust GC policies that we could easily plug into and demonstrate some of the benefits of Rust-based garbage collection. So our Python is restricted Python. It supports all the syntax of Python, but it is statically typed and is able to do manipulation of very low-level manipulation of objects and addresses. So there was a compromise. They had to make a compromise in Python to be able to do those low-level manipulation to the objects. So what is MMTK? MMTK is the Rust-based garbage collection framework that's going to be the main focus of my talk today. It did not begin as a Rust project, as most projects are these days. We seem to rewrite everything. So we had some language, and then when Rust came, we said, oh, now we are rewriting everything. So the history of MMTK is such that it's almost 2 decades old, almost 20 years. It started as a research project, and MMTK initially was written in Java, and its design was highly tied to the JAX RVM virtual machine, which was a Java implementation at the time. And the work for 2 decades in MMTK gave us a lot of insight into garbage collection research. MMTK allowed the researchers to come up with new garbage collection policies, but they were demonstrating their work mostly in the Java ecosystem, because MMTK at that time was very tied to JAX, which is Java. Now, several years later, one of the researchers on the MMTK team wrote a paper or did an experiment about porting or having an MMTK implementation in Rust. And the results were very interesting. And at the end, as documented in this paper, you can read it, the experiments showed that Rust was actually a great language for implementing very high performance GC, garbage collection functionality or policies per se. And at that time, we could do this, but and while breaking very minor safety guarantees of the language. And this paper is almost 10 years ago. And the results of this paper led to that team to rewrite MMTK from Java into Rust. And now MMTK, the default MMTK memory management toolkit is now shipped as a Rust project and no longer a Java project. So what's MMTK? MMTK contains of 4 main parts. Whatever you see in pink is MMTK, which is MMTK core, which is the library implemented in Rust and served as a Rust crate that people can use to implement garbage collectors for different programming languages. And another aspect of the runtime in pink is the runtime bindings, which is a language-specific code that uses an MMTK. Remember, MMTK is a library designed to be very language independent. So it does not have any details of a programming language like Python, details like the object model. So if we want to know aspects about the object model of a language like Python or Ruby or OpenJDK, we have to use the bindings to write that language-specific code, but the bindings call back into MMTK, which is much more general. So on my left, some white boxes, which is now the runtime specific code. We will have like runtime bindings as well. So there are features that have to be written in the language side, but to interface to MMTK. So we would call that runtime or language bindings, and I'm going to go very deep into detail on that. Then we'll have, of course, the runtime code, which is an interpreter or language code itself for garbage collector, to do a garbage collection that calls into the bindings and eventually into MMTK. So what's the core? MMTK core, as I've already hinted earlier, was designed with 4 key principles. One, of course, it's written in Rust, served as a crate, and it was written to have high-performance DC policies. So for 20 years, all the research that was done in the Java ecosystem has informed MMTK over the years to come up with garbage collection plans and policies that are very finely tuned to handle different workloads. So it's using knowledge of 20 years to come up with policies that could work here very favorably for different languages. Of course, there is no one garbage collection policy to rule them all, but we try to have a fine balance between the two. Second and most important is they try to make the aspect of garbage collection language independent. We have been used to every language implementing their garbage collector, but we know that if you've ever written a garbage collector, it's a very complicated task. It's not something you write in a day or two. So if we thought about it being a good idea, that if we brought out this complexity and put it in a sort of a library in a more language independent way, then we will make writing new garbage collectors a very feasible option for language implementers. And we made sure that we do not tie the implementation to a particular language. Of course, portability, due to the modular design of MMTK, it's able to be used for different runtimes and different developers. And lastly, correctness. With something as complex as a garbage collector, if you reduce the barrier to starting a new project in garbage collection, then you lessen the aspects of like any bugs that could be written if you're writing a GC from scratch. But if you're calling libraries, then the guarantees of writing more correct or code with less bugs is a little bit higher. So those were the 4 main objectives when MMTK was rewritten or written 20 years ago. So this is a sort of the almost the same hierarchy. This is a hierarchy of how MMTK is used. I just brought it out in more concrete terms, what it means for runtimes that consume MMTK. So we will have runtimes like Julia on my left in purple. Then we have bindings, the orange bindings are the bindings that are in the runtime that specific for MMTK. So code in the runtime that calls MMTK in white. Those are the different bindings for Ruby, but on the MMTK side, responsible for things like scanning and other things. So concretely, this is what a core binding looks like. Because MMTK is written in Rust, bindings that have the knowledge of like the object model of the language have to also be written in Rust. So MMTK, or what I call core bindings, are also written in Rust, but they have knowledge of the language. So that's what we call core bindings. Runtime bindings are written in the language in which the runtime is implemented in. For example, for PyPy, these bindings are supposed to be written in RPython. But for performance reasons, as you can see, this is actually C++. This is not RPython, because in PyPy, for certain very performance critical routines, we can write C or C++ for those aspects. So this is actually C++ code for spawning a thread to handle collection. Because MMTK needs to know roots, because the runtime needs to give it roots and many other things for it to work on. So this is runtime code written in the language of the runtime, but calls into MMTK. Then finally, the runtime code, which is the actual garbage collector code. Now this is written in RPython for this example, because this is PyPy, and because we call Rust, at the end of the day, most of the logic we call Rust, we have to have call Rust through C, some sort of, but because it's Python, we have to do RFFI of some sort. And PyPy supports its own FFI interface to call into C and other things. This brings a little bit of bottleneck, as I'll talk about later, but our results have showed benefits either way. So MMTK, as I already said, it's already been demonstrated in production for different languages, and currently there is a lot of work going on that's porting MMTK garbage collectors into different runtimes. There is Ruby work, there is Julia, there is OpenJDK, and the OpenJDK work is much more advanced because it's taken a little bit more time, and the MMTK GCs have shown to outperform some of the default GCs in OpenJDK. But today I'll talk about PyPy, because that's the team I've been working with, and that's what I work on. So inside PyPy, what happens? We took a different design. We did not really follow the design I've just talked about earlier, because it did not work very perfectly with PyPy. We could not achieve that separation or abstraction of bindings especially. So we ended up mixing the runtime bindings and the core bindings into one, because that separation was not possible because of how PyPy is written. So PyPy features RPython, which is a framework that is used to translate or to develop other interpreters or other dynamic languages. So garbage collection is hooked into that framework through some form of transformation. So having very clear-cut separation of the binding code was not easy, but nevertheless, it did not require editing MMTK to make it have PyPy details, for example. So we still have core, the MMTK core, and one binding layer, which is a mix of core and runtime bindings, and then the runtime code. So the blue blocks is the RPython translation toolchain. Language like PyPy is written in RPython. It's compiled to bytecode, and this bytecode goes through a phase where we convert it into control flow graphs. So the control flow graphs go through type inference, where all the variables are given types. Then it goes through a phase of transformations, which transformations make the operations of the control flow graphs look much more closer to a target backend. Then, of course, the RPython translation toolchain converts this bytecode that's now a control flow graph into a target backend like C or any other object-oriented backend. So PyPy, the interpreter, is written in RPython, but it's compiled to C, not to an OOP backend. So we tap into the transformation phase of this RPython toolchain to support the MMTK garbage collection. So we write an MMTK-based, whatever we call a transformation, to tap into these operations in the control flow graph and replace any memory management related calls in the program as it's getting translated to call into our garbage collector. I'll give an example. So we tap into all the allocations or malloc operations in the process of before we convert to the final backend, we convert all mallocs to allocation calls in the actual garbage collector. So MMTK alloc replaces malloc operations to do the allocation. And collection is also the same. So we implement a transformation and implement the actual garbage collector because the transformation just maps calls. And then, of course, we have the MMTK bindings. Very useful in the PyPy toolchain is the tracing JIT that's in there. So we have to do also a lot of work into integrating the GC operations to the JIT. And JIT integration involves like two main parts, the front-end analysis and the back-end analysis. So the front-end analysis just generates traces because a tracing JIT just generates all the traces of the operations involved as a program is running. And so for the garbage collector, what we have to do is to generate all the GC operations in the trace and make sure we convert them to a lower level language that's something we call REST operations that are then sent to the backend. And then the backend does some rewriting of these GC-related operations in the traces. An example of a rewrite of these traces could include, because when we map the allocations, the malloc to the MMTK allocations, we will have like multiple allocation operations in the traces. So one example of a rewrite would be combining all those allocation operations into one, and several other optimizations that could happen in the rewrite during the back-end analysis. So I think it's basically for PyPy, it's simple. We follow the normal MMTK business, but the tracing JIT brings some other complexity. So I have gone through a little bit of the JIT integration, and maybe the only thing I can complement here is the GC reference tracer, is that we also go through all the traces, and we identify GC pointers that point to constants and try to replace them with their actual values as an optimization at the backend. And so the actual work of rewriting we rewrote about 4 garbage collection policies the PyPy GC policies to use MMTK. As you know, we were calling a library, so the difficulty or the effort was not too much. So the effort is debatable because we call a library, like I said, we have a whole layer called bindings, but this is also code we are writing, right? So it's less effort, but not really less effort as well due to what we do in the bindings. But then in general, we did not have to, we didn't write a garbage collector from scratch. At its core, that's what happened. The savings in the amounts of code were there if you care, if you're a software engineer and you like doing the math for like cyclomatic complexity and we almost wrote half the code. If you looked at the RPython files we were creating, if you compare that to RPython code, we wrote half the code because we were calling MMTK, which is a library. The code, due to modularity, the MMTK GCs were more maintainable. We could see the maintainability index is better. The resulting code is easier to maintain than the existing GCs we had in there. And due to correctness guarantees we get from MMTK, maybe we are able to write less bugs in that regard. This we are not able to quantify. We are still struggling with some bugs as well, but we hope that because we are calling correct code, this is less likely. So in terms of performance, we did some benchmarking for the standard Python benchmark suite. So we used PyPy with our garbage collectors that use MMTK against the default PyPy GCs. And in terms of mutator time, it was not a very good story. We saw a bit of overhead that was between 25 to 35%. This is not necessarily because of MMTK. In fact, for 20 years, MMTK has very many optimizations. So most of the overhead was around the allocation. I can't separate allocation and mutator code. It's hard to do that performance. So mutator code includes allocation time. So most of the overhead is in allocation. We optimize that. In fact, before the optimization for allocation, the slowdown was almost five times slower, but with that optimization of the fast path and slow path for MMTK, we improved this. So the overhead in mutator time is attributed to how we interface the Python to Rust, right? There's that overhead of RFFI that we can't do away with. It's just a constraint in how the language PyPy is implemented in. And however, when I looked at GC time, this is where we can also conclude that actually using a GC that's implemented in Rust brings performance because MMTK GCs were performing better in GC time, the time it took to do collection, and by a magnitude of 6 to 10%. So we don't dispute that aspect. The paper was actually right. We got some benefits in using a Rust-based GC. Of course, the mutator time overpowered the overhead we saw in the mutator time, overpowered some of the benefits we got in GC time. Again, the reasons is because of interfacing Python and Rust. Yeah, so we see similar overhead between 2% to around 17% in total for especially very memory critical benchmarks like binary tree and the like. So what are the key insights here is that, of course, as I say, the paper was right. We saw some benefits in calling MMTK GCs. Of course, we break some safety guarantees, and we can't quantify. The paper told us certain aspects of Rust that are good for implementing garbage collectors, like safety and the rest of the things. Those we can't quantify for now. I don't think there is a silver bullet for now. but also interfacing Python to C still shows a little bit of overhead that we can't ignore. MMTK has the slow path and fast path for both write barriers and allocations, but still we call into the slope. We have to call the MMTK library at some point, so we can't do away with that overhead. With that, I would love to end my presentation, and thank you all, and I'll be around for any questions on MMTK.